We're going to close out chapter 16 with part 2 of section 16.4, where we're going to talk about temperature and equilibrium as that relates to this delta G or Gibbs free energy. So there's your learning outcomes and expectations. Feel free to pause and read through that. All right, like we said previously, 16.4 is a pretty hefty section, so we partition it into two sections. First, we talked about Gibbs free energy, and now we'll talk about temperature and equilibrium and how that relates. And so we have this delta G, which allows us to define the delta S of universe in terms of things we can measure, delta H system and delta S system, via this equation, the Gibbs free energy equation, where delta G is equal to delta H system minus T delta S of the system. And so when thinking about the different relationships you can have between delta H and delta S of a given system, you can have a negative sign on delta H and a positive sign on delta S. In this case, it's entropically favorable. The entropy is increasing in this system, and it's enthalpically favorable. It's exothermic. It's releasing heats to the surroundings. And so we can look at the signs on these, even without actual numbers, and we can say, is this process going to be favorable? And one of the things that enables this is T is always in Kelvin, so it's always a positive value. And so essentially, if this is positive, this is negative, a positive times a negative, or a negative minus a positive, is always going to give you a negative value, which means it's always going to be spontaneous. And that makes sense. It's entropically favorable, enthalpically favorable. Both these parameters are favorable, and so it's always going to be spontaneous. Conversely, we can have a scenario where it's entropically unfavorable, where the entropy of the system goes down. We have something that's enthalpically unfavorable, where it's an endothermic, it steals energy from its surroundings, and that is always going to give you a positive value of delta G. I apologize, this should be a positive value. It's always going to be non-spontaneous. But you have these scenarios, these mixed scenarios, where you can essentially have enthalpically unfavorable and entropically favorable, or you can have enthalpically favorable and entropically unfavorable, and both of those will give you a negative or positive value. It's going to depend on this temperature. All right, you can think about this temperature as a modifier and dictating how important this delta S system, or how much this unfavorability or favorability impacts this delta H system. And so we already know this. We already know reactions can be a temperature-dependent phenomena. We know that spontaneity is a temperature-dependent phenomenon. Why do we know this? Because we experience this regularly, right? So if we take some ice, this solid H2O, and we put it out at room temperature, it will spontaneously turn into liquid. Alternatively, if we take this and put it in a freezer, we know that it'll spontaneously turn into a solid. And it's because of the temperature dependence. If the temperature is greater than 0 degrees C, it's spontaneous one way. If it's less than 0 degrees C, it's spontaneous the other way. And so this is one of those scenarios where it is temperature dependent whether this process will occur. And it really comes down to this T, right? This delta H and delta S is the same regardless if you're going solid to liquid or liquid to solid. The thing that's really changing is this T and how much this T impacts this process. And so looking back at the pairs, we have favorable, favorable, always spontaneous, unfavorable, unfavorable, this should be positive, always non-spontaneous, favorable, unfavorable, it can be negative or positive. It's going to depend on the temperature of the reaction. And so let's look at the possible scenarios of this. So we have entropically favorable, the entropy of the system decreased or increased, and enthalpically unfavorable, it's an endothermic process or a positive delta H. And so looking at these values, we have a positive delta H system, we have a positive delta H delta S system, and so this temperature is really going to dictate which one of these wins. Is it the positive value over here, or is it the overall negative value here? And so looking at the possible relationships, if T is large, if we make that temperature high enough, it basically says we have a negative, a positive times a positive, and a negative sign in front of it. And so this is going to be a large negative number, right? The larger T, the larger this negative number will be. If that negative number is large enough, it's going to be greater than the positive delta H system. And so if this T is high enough, and this is a positive delta S system, this is going to be a large negative number. Overall delta G is going to be negative. And so this type of reaction, where it's enthalpically unfavorable and entropically favorable, becomes spontaneous at higher temperature, because this T in this negative sign makes this a larger negative value, which gives you an overall negative delta G. Conversely, if temperature is low enough and that value becomes low enough, you're going to get a small negative number, right? If this number is small, this delta S system, positive times a positive, you're going to get a smaller number here and a smaller negative number here, which means when you add that with the positive delta H system, at some point this is going to win out that battle where this positive is larger than the negative is here. And so you're going to give a positive delta G. And so the reaction becomes non-spontaneous at lower temperatures. So to recap, we have a positive delta H, we have a positive delta S. Those two are competing. This temperature is going to dictate which one of those two wins. Is it the favorable or unfavorable? And so at larger values, this delta S system wins. At smaller values, the delta H system wins in terms of being unfavorable, which means the process will be non-spontaneous. And so you can do the same exact thing with this entropically unfavorable and enthalpically favorable, where this is favorable, it's exothermic, but the entropy went down. So this is an unfavorable process. And so again, this T is going to dictate which one of those wins. So at higher values of T, we have a positive times a negative number. The bigger this number is, you're going to have a large positive number because this negative sign will cancel out with this sign. And that number is going to be largely positive, and that's going to beat out this negative delta H system to give you a positive delta G, or a non-spontaneous process at higher temperatures. Conversely, if this T is small, where we have a small number times a negative delta S system, which means we're going to have a small positive number. If this delta H system is sufficiently negative, then that's going to win, and that gives you a negative delta G overall, and the reaction becomes spontaneous at lower temperatures. And so, yeah, this is a lot of signs to go through, but the idea is you have a negative here, and so you have a negative sign in between them. This becomes positive. The question is, how much positive is it? If it's very positive, then you're going to have this. This is going to win, and you're going to have a positive delta G. If this is a smaller temperature number, this is going to be a smaller positive value, and this negative delta H is going to win, and it's going to primarily dictate delta G. And so, yeah, go through those signs and those relationships, and that allows you to predict at high temperature, low temperature, which one's going to win. Is it the favorable or unfavorable process? And so if you want to do this in tabulated form, again, I wouldn't recommend memorizing this, but there's basically a limited number of combinations that can occur. Right, you can have, an endothermic reaction, which is an unfavorable delta H. You can have an exothermic, which is a negative delta H, which is positive. Increase in entropy is favorable. Decrease in entropy is unfavorable. And so if it's unfavorable, if it's favorable, it's always spontaneous. If it's unfavorable, it's always non-spontaneous. And then here in the corners, you have every mix and match between. At high temperature, it's favorable, low temperature, unfavorable, or vice versa, depending on the signs of those individual delta H and delta S's. All right, so it turns out this becomes pretty useful in terms of you can actually figure out when a process will change from non-spontaneous to spontaneous. And so we saw earlier we can take, solid H2O turning to liquid H2O and liquid H2O to solid H2O, and that happens at 0 degrees C. Well, it turns out you can figure out when that temperature is. You can actually figure out boiling points and melting points from these delta G values. And so let's take an example here. We have Br2 liquid going to Br2 gas. There's the delta H, there's the delta S. We can get those from tabulated values. And so we can actually figure out when is this process going to turn from spontaneous to non-spontaneous. And so we want to essentially know what temp does Br liquid turn into Br2 gas? When does it become spontaneous? This is effectively finding the boiling point of Br2 liquid. And so here's our equation here. Essentially what we know is that the transition from non-spontaneous to spontaneous is going to happen when delta G is equal to 0, right? Because on one side it's negative delta G, spontaneous. On the other side it's positive delta G, it'll be non-spontaneous. And so if we set delta G to 0, we're effectively figuring out when does that transition occur. And so looking at this equation, we rearrange it slightly. Temperature is equal to delta H over delta S. We have delta H and delta S values. We can plug those in. We can do our calculations. And we find the temperature of 331.5 Kelvin. This is when that transition occurs. And so it basically says at 331, we're going to transition from non-spontaneous, liquid doesn't go to gas, to spontaneous, where the liquid liquid goes to gas. That 331.5 is the predicted boiling point based on these delta H and delta S values. And so it turns out that ends up being really, really accurate in terms of predicting when this boiling point will occur, because it's the transition from non-spontaneous to spontaneous. Similarly, if we cool down below that value, we're going to get the condensation. We'll get the gas going to liquid, because that's the phase transition temperature. All right, so changing directions a little bit, still talking about Gibbs free energy, but we're talking about Gibbs free energy in the context of an equilibrium. And so we've drawn this equation over and over again, A plus B giving you C plus D. Products minus reactants gives you the delta G of the reaction. And so that delta G of the reaction tells you spontaneity. And so spontaneity in this case means, does it favor products? If it's negative delta G, yes. If it's a positive delta G, it actually favors reactants more than products. It basically says the reverse reaction is spontaneous. And so that's important because we're relating this delta G value back to equilibrium. And so just because a delta G is negative, it doesn't mean it's always going to go to products. Similarly, if delta G is positive, it doesn't mean it's all going to stay as reactants. You're going to have a balance of those two. And so this goes back to the idea of equilibrium, right? Negative delta G tells you it favors products, but it doesn't tell you only products. Similarly, a positive delta G favors reactants, but it doesn't tell you there will only be reactants. And so what we're really talking about here is an equilibrium condition. We're saying, delta G tells you which way it favors, but it doesn't say it favors only one or the other. Instead, it tells you how much driving force there is to go one way versus the other. How much does it want to go towards products versus reactants? And so here's the equation that actually relates those two. And so in chapter 13, 14, and 15, we talked a lot about this equilibrium constant K. Well, it turns out what's driving that K is this delta G. It's telling you whether it's favorable to make products or it's favorable to make reactants. And so looking back at this equation, a lot of these things should look familiar. This K, this is our equilibrium constant. It could be any of the equilibrium constants we've talked about. We have temperature, we have a gas constant, and we have this free energy, or Gibbs free energy, this delta G naught, which is a standard free energy term. And so looking at this equation, and we can plug and chug any numbers we want, we can basically see there's a relationship between delta G and K, right? And so in this case, we're going to do the math for 337 Kelvin. It basically says, your delta G is positive, which means it's non-spontaneous in the forward direction, which means favors reactants, which also means we should have a small K value. It favors the reverse reaction. It does not favor the forward reaction, so we should exist as mostly reactants. And that's exactly what you see with this K value, right? 9 times 10 to the minus 36 heavily favors reactants, and it does so because there's a positive delta G. And so if we're going to draw a reaction coordinate diagram with delta G on the y-axis, we'd basically say, in terms of Gibbs free energy, note this is not delta H, this is delta G. It would be heavily uphill to go to products. And so what this tells us is things would much rather be reactants than they'd rather be products. And so we could go to the other extreme. We can look at it and say, okay, if it's a negative delta G, that means it's spontaneous in the forward direction, means it heavily favors products. And that's exactly what you see here, 1 times 10 to the 35th. It wants to be products 35 orders of magnitude more than reactants. And the reason is because there's a negative delta G. And so drawing the reaction coordinate diagram in delta G, we can see products are much, much more favorable. And this delta G is basically the difference in driving force for generating products versus reactants. And so that's where it comes from, right? The K value tells us, does it favor products or reactants? The reason that K value is the way it is because this delta G tells us that it favors products over reactants, or it's spontaneous in the forward, and this one's spontaneous in the reverse direction. And so somewhere in between, you can have an equilibrium constant of 1 where it favors both of them comparable extent. And so you'd essentially have a 0 delta G, which gives you an equilibrium constant of 1. It favors reactants and products essentially the same. And so there's no reason to go one way or the other. And so, yeah, if you have a positive delta G, it's going to favor the reverse reaction, or you'll have a very small K. If it's a negative delta G, it favors the forward process, which gives you a large equilibrium constant K that favors products, and then everything in between those. And so it's really this thermodynamic driving force that dictates what condition does it reach when the system reaches equilibrium. And so, yeah, really important relationships. This delta G naught is equal to negative RT natural log of K. It tells you which way it favors, right? And so if it's a negative value, it's spontaneous under standard conditions, which means it favors products and generates more products and gives you a larger K. If it's positive, it's non-spontaneous in the forward direction, which means it favors reactants, and you have a lot more reactants and you have a smaller value of K. And so in this case, it's going to be a K less than 0, and then in this case, it's going to be greater than 0 or 1. And so this delta G, it's kind of an interesting concept, but it basically tells us how favored reactants and products are, right? We saw that from those tabulated values previously. The more negative it is, the more it favors products. The more positive it is, the more it favors reactants. And so it tells us the favorability of those. And so one thing to note about this, and we've seen this over and over again, we have this not symbol, right? And here it's highlighted in blue. It's basically the standard free energy of formation, or standard entropy, or standard enthalpy of formation. And so if you look at the formal definitions, the standard free energy of formation is the free energy change occurs when 1 mole of the compound is formed from its elements. And so what we've basically done is we have to pick a condition to use as our standard. And it's basically a reference point that says we're going to compare everything versus this standard condition. And so what we've as a community decided on, the standard condition is the list here, right? And so it's liquid, solids, and gases are pure, 1 molar solutions, 1 bar for gases. This is the standard temperature. 1 mole formed from a constituent elements in terms of the formation, the delta H formation and delta G formation. We've basically created a frame of reference that we can say, if we start on these standard conditions, what is the driving force, the delta G, to do this forward process? Is it favorable? Is it unfavorable? But what if you're not at standard conditions? And so we've come across this before when we've talked about Q versus K. K is under, equilibrium conditions, the system's content. But if you're not at standard conditions, you have to modify this slightly. And so this calculation here, it says under standard conditions, this is the delta G value, and that's how it relates to K. But if you're not under standard conditions, all of a sudden we have this Q, right? This non-standard condition where we say, what condition is it at? And what is the driving force for it to get to equilibrium? And that's this delta G. And so this delta G naught is under standard conditions. That's the relationship between delta G naught and K. But under non-standard conditions, there's a certain drive to get to that equilibrium. And that's what this delta G without that naught tells you. It says under non-standard conditions, what is the driving force to get to those standard conditions? And so looking at this equation, again, should be familiar. We have the reaction quotient Q, temperature, gas constant. We have the standard free energy, which we get from tabulated values. It says, if everything's at 1 molar, what's the driving force to get to that equilibrium? If it's negative value, it's favoring products, positive value, it's favoring reactants. But this delta G basically tells us if we're not at those standard conditions, what's the non-standard free energy to get to those conditions? And so we can insert this equation here into here and get this relationship here. Again, we don't emphasize plug and chug in this class, but essentially what this allows us to do is figure out the delta G that drives the system to equilibrium. And so we have this K condition at equilibrium. We have this Q that's a non-standard condition, and then this delta G tells us the driving force to get to that equilibrium. And so if Q equals K, delta G is 0. It essentially says, it's at standard condition, or here's the driving force from standard condition, and the reaction is at equilibrium. If Q is less than K, then this delta G, note there's not a not sign here, it's going to be a negative. It's going to tell us it's going to shift towards products. If Q is greater than K, the delta G is going to be positive. It's going to shift spontaneously towards reactants. And so this is the same rules we talked about earlier. If Q is less than K, it shifts to the right or towards products. If Q is greater than K, it shifts to the left towards reactants. Now, note the difference between delta G and delta G naught. Delta G naught tells you overall when it reaches equilibrium, is it going to favor products? Is it going to favor reactants, right? What this delta G without that naught sign, it says, which way is it going to go? Is it going to go towards products? In this case, a negative delta G tells us it goes towards products. A positive delta G tells us it goes towards reactants, or it shifts in that direction. But it doesn't necessarily say we're going to generate more products. That's what delta G naught tells us. It tells us the amount of products we'll get when we reach that equilibrium condition. This delta G just tells us which way it is going to shift to get towards that equilibrium condition. All right, so closing out chapter 16, we've seen that a reaction can be enthalpically favorable or unfavorable, a negative delta H versus positive delta H. Similarly, it can be entropically favorable, a positive delta S system, or unfavorable, a negative delta S system where the entropy decreases. We can have a bunch of different scenarios. For example, if it's enthalpically and entropically favorable, it's always spontaneous. If it's enthalpically and entropically unfavorable, it's non-spontaneous. If you mix and match between those two, you have a favorable and an unfavorable. It's going to depend on the temperature of the system. And so it depends on how big that T is and which one wins. Is it the delta H or the delta S and the sign associated with those? And so it can be spontaneous or non-spontaneous depending on the temperature of the system. We can also use this to our advantage to calculate when spontaneity is going to occur, right? When will it go from non-spontaneous to spontaneous or vice versa? And we can do that by setting delta G equals to 0. That's the threshold when it goes from spontaneous to non-spontaneous. And you can use this to predict, when a reaction will become spontaneous. You can use this to predict boiling points and freezing points and things like that. All right, then we transition to talking about this delta G naught and how it's related to the equilibrium constant K. Delta G naught is equal to negative RT natural log of K. If delta G is a negative number, it favors products. If it's a positive number, it favors reactants based on this relationship here. And then we also talked a little bit about non-standard conditions, where delta G naught is standard conditions, delta G is non-standard conditions, and it basically relates this Q and K, right? Where Q is less than K, it shifts to reach that K condition. This is the reason it does. That's delta G is essentially the driving force, or which way will it shift spontaneously to proceed towards that condition. And so, yeah, relating a bunch of those variables together. All right, so that closes out chapter 16, thermodynamics. Next, we'll start diving into electrochemistry.